You have seen the most terrifying storms on Earth. Hurricanes that flatten cities, typhoons that swallow coastlines. But imagine placing those monsters next to the weather on Jupiter. What you think you know about storms is not even a whisper compared to the reality out there. Everything we call extreme is just a tiny, fragile version of what is waiting beyond our sky. So let's look closer at the forces we have completely underestimated. There is a storm on Earth so powerful it can level entire cities in a matter of minutes. It is the kind of force we are taught to fear, the absolute peak of nature's fury. But what if you took that storm and placed it next to the weather on Jupiter? The most terrifying storm we can imagine is nothing more than a gentle breeze compared to what is happening out there. Everything you think you know about hurricanes and cyclones is just a miniature version of a far greater reality. The truth is that our planet's most violent weather is dwarfed by a single ancient entity that has been raging for nearly 2 centuries. Let's look at the facts about what we call the Great Red Spot. This is not a typical storm. It is a massive anticyclone, a weather system that rotates in the opposite direction to the planet's atmospheric flow. According to NASA, this colossal feature is wider than the entire diameter of Earth, measuring approximately 16,000 kilometers across, and it has been continuously active since at least 1830. In 1979, the Voyager 1 spacecraft flew by Jupiter and gave us our first close-up look. It revealed swirling details and satellite storms around the Great Red Spot that ground-based telescopes could never detect, completely changing our understanding of giant planet weather. The sheer scale is hard to process. You could fit our entire world inside this single storm with room to spare. Consider the wind speeds at its edges. While a Category 5 hurricane on Earth tops out at around 252 kilometers per hour, the winds on the rim of the Great Red Spot range between 430 and 680 kilometers per hour. To truly grasp the difference, you can compare these numbers directly. If you could somehow lift the Great Red Spot from Jupiter and place it over our planet, it would swallow entire continents whole. Our most devastating storms would look like tiny ripples in a puddle next to this eternal monster. This storm doesn't just break records, it redefines the meaning of the word. Here is the script for Part 3, written in English, adhering to all the specified constraints. But here's where the story twists. Every image you've seen of the Great Red Spot, every awe-inspiring photograph, is a snapshot of something that is dying. Or at least that's what the data seems to say. Measurements gathered by NASA and the University of California show a dramatic transformation. In 1890, this storm was a staggering 41,000 kilometers wide, a monster 3 times the diameter of Earth. By 2023, that same tempest had shrunk to roughly 16,000 kilometers, barely 1.3 times our planet's width. Over 130 years, it has lost more than 60% of its original size. Shrinking storm fits our earthly logic perfectly. It suggests a loss of energy, a slow decay toward a final quiet end. The natural conclusion is that the most famous weather system in the solar system is on its last legs. But the latest science suggests we are looking at it all wrong. The storm isn't dying, it's evolving. Researchers at UCSC have found that while it contracts horizontally, it is growing taller. The winds at its periphery haven't slowed one bit, still screaming at speeds around 600 kilometers per hour. It's as if a figure skater is pulling their arms in. The total size gets smaller, but the spin gets faster and more intense. This is not the behavior of a storm fading away. This is a storm consolidating its power, becoming denser and more concentrated. The shrinkage is a restructuring, not a disappearance. And if you want proof that Jupiter is still a violent factory of weather, you only need to look at what happened right next door in the year 2000. 3 white storms, first spotted by amateur astronomers back in 1938, were drifting toward each other in the same latitudinal band. Over the course of that year, they collided and merged into a single, larger feature. This new entity, named Oval BA, was almost a direct copy of its giant sibling. At first, it was white, just as before. But then came the shock. By 2006, scientists were stunned to see that Oval BA had changed color, turning a deep, rich red. It had become a second little red spot, a clear demonstration that this gas giant is still birthing colossal, planet-sized monsters in real time. So what is fueling this Titan's relentless power? What engine is strong enough to reshape a storm that could swallow continents? And what will it create next? To understand why Jupiter's storms dwarf anything on Earth, you have to stop picturing weather as something that happens on a surface. Start with a simple comparison. Take the most powerful hurricane you can imagine, then multiply its energy by the sheer scale of an entire planet. The first step is to acknowledge that a terrestrial storm is a shallow phenomenon, a thin skin of wind spinning atop a solid sphere, whereas a Jovian storm is a deep feature, anchored thousands of kilometers into the gas giant itself. The data from NASA's Juno mission rewrote the textbooks here. showing that the planet's jet streams, those bands of wind that wrap around the globe, plunge roughly 3,000 kilometers into the interior, which is several dozen times deeper than researchers previously believed possible. So the real question becomes, what kind of engine can drive winds that deep? It turns out the answer is not the sun, but the planet's own core. Jupiter radiates 1.5 times more heat into space than it receives from sunlight, a fact documented in Nature Geoscience in 2018, a surplus generated by the slow gravitational contraction known as the Kelvin-Helmholtz mechanism. That internal heat rises, churns the deep hydrogen, and feeds the atmospheric bands above, meaning every storm on the surface is just the visible crown of a colossal convection system. Picture the math. This is a planet that is itself the fuel source, with a heat engine that has been running for over 4 billion years. And here is the twist that breaks your mental model completely. There is no solid ground anywhere beneath the clouds. Juno's data, published in Science in 2018, revealed that Jupiter has no solid surface at all, with pressure and temperature increasing steadily until, around 13,000 kilometers down, the hydrogen gas compresses into a liquid metallic state. So when you look at the Great Red Spot, you are not seeing a storm that hides its roots underground. You are seeing a storm that is the planet. And the planet is the storm, a single, living, and violently self-sustaining weather system. Here's a way to imagine it. The only reason we think of Jupiter as a frozen, distant world is that we assume distance from the sun dictates temperature. That assumption shatters the moment you measure the air at its poles, where the upper atmosphere blazes at nearly 700 degrees Celsius. To put that in perspective, that is hotter than the surface of Venus, a planet where lead head would melt on the ground, and it rivals the heat you would find on the sun-facing side of Mercury. The real shocker is that this inferno is not coming from the sun at all, because Jupiter receives barely 4% of the sunlight that reaches Earth. The answer lies in a violent interaction between the solar wind and Jupiter's massive magnetic field, which creates shock waves that slam into the atmosphere from above. Those shock waves, combined with powerful auroras at the poles, dump energy into the upper atmosphere, heating it to temperatures that should be impossible at that distance. During a 2016 mission, NASA's Juno spacecraft had to cross the most intense radiation region of Jupiter during a 35-minute braking burn. Had that maneuver failed, the probe would have been flung past the planet into deep space forever. It survived the crossing, and its data revealed that Jupiter's upper atmosphere is not a cold void but a raging furnace driven by forces completely alien to our own planet. You might think a diamond rush in space would be the ultimate jackpot, but the reality on Jupiter is a cosmic cruel joke that crushes every get-rich-quick fantasy. Let's walk through the recipe, step by step, starting with Jupiter's atmosphere itself, which is roughly 90% hydrogen and 10% helium, with a splash of methane mixed in. Deep below the visible cloud tops, the pressure becomes so intense that it compresses that methane into carbon atoms, first forming flakes of graphite, much like the lead in an ordinary pencil. As those graphite flakes sink even farther, the immense pressure and heat transform them into actual diamonds, creating a literal shower of gemstones. Now, here comes the punchline that shatters all our dreams. Scientists at NASA estimated that Jupiter and Saturn could generate about 1,000 tons of diamonds every single year through this exact process. Before you start calculating your share, stop right there, because this treasure trove sits at a depth of tens of thousands of kilometers, where the temperature reaches a hellish 8,000 degrees Celsius. At that heat and pressure, any mining machine we could possibly build would melt and be crushed before it even touched a single gem, making the greatest treasure in the solar system utterly untouchable. So we can't harvest them, and that raises an uncomfortable but fascinating question. Are there other secrets hiding in this stormy atmosphere that defy everything we assume about weather and wealth? Imagine the most violent storm you can, and now strip away every limit you have ever known. On Earth, we measure destruction in hours and kilometers, but Jupiter measures it in centuries and continents. The auroras alone stretch wider than our entire planet, casting a ghostly light that would swallow the Atlantic Ocean beneath a single curtain of charged fire. And these lights do not come from the sun. They are born from Io, a moon that vomits volcanic material into Jupiter's magnetic field, creating a spectacle with a completely different origin than anything we see in our polar skies. So, how can a moon trigger a light show that dwarfs our world? The answer lies in a mechanism foreign to our own atmosphere, and it gets stranger. We have also discovered lightning on Jupiter, but not the kind you know. Ordinary storms flash near the cloud tops, yet here there is another breed. According to a 2018 study in Icarus, Jovian lightning can strike in shallow ammonia clouds and also deep within water clouds, hundreds of kilometers below the visible surface. That means the same planet hosts two distinct types of electrical storms, each operating at pressures and temperatures that would crush and vaporize any earthly probe. The atmosphere is not merely a weather system, it is a non-stop physical reactor. And every flash and glow you could ever admire would kill you in an instant. Jupiter's magnetic field is not just big, it is an absolute monster. It is roughly 20,000 times stronger than Earth's, creating a radiation environment that is lethal to unprotected electronics. This invisible death trap is the first and most brutal barrier any spacecraft must survive if it hopes to study the king of planets. To truly grasp the danger, you first have to understand what the spacecraft is flying through. The radiation within Jupiter's particle belts is a full 10 times more intense than anything found in Earth's Van Allen belts. It is not a subtle difference, it is a fundamental shift in scale, a region where the very fabric of space is saturated with high-energy particles moving at near-light speed. Let's put that intensity into a perspective that makes sense for a human body, not just a machine. Imagine going to the dentist for a single X-ray. Now multiply that exposure by 100 million times. That is the dose of radiation Juno's electronics are subjected to with every single pass around the planet. It is a level that would fry an unprotected computer chip in an instant. So how does a fragile human-made probe survive such a constant barrage? The answer is a masterpiece of engineering, a vault made of titanium. Weighing in at 180 kilograms, this armored container acts as the spacecraft's heart, shielding its most critical flight computer and sensors from the relentless assault. It is the only reason Juno can operate at all in this extreme environment. In September of 1859, the most powerful geomagnetic storm ever recorded slammed into Earth, and it announced itself in the strangest way. Telegraph operators in Europe and America watched as their equipment burst into sparks, even with the power supplies disconnected. A Boston operator was knocked to the floor by a shock that came straight down the wire from the sky, proving that weather is not confined to the thin shell of air we breathe. But what would happen if that invisible force, powered by our own sun, were turned up 100 times over? This is where the conversation shifts from an academic curiosity to a matter of pure survival, and it introduces a new scale of danger that makes a hurricane seem like a gentle breeze. To understand the threat, you first have to understand the warning system, which is a 5-level scale known as G1 through G5. A G1 storm might cause a few minor fluctuations in power grids, while a G5 is the nightmare scenario that could melt transformers and leave continents in darkness. The Carrington event was so violent that it would have easily registered as a Category G5, tearing through the planet's magnetic field with a ferocity we have not seen since. In 2023, NASA and the European Space Agency, using the Solar and Heliospheric Observatory, witnessed a warning shot fired from the Sun's surface. They recorded a coronal mass ejection that was roughly 100 times more powerful than the typical storm response responsible for the 1859 event. The cloud of charged particles missed Earth, but the data revealed a terrifying truth about the fragility of our modern existence. Had that blast hit us directly, it would have overwhelmed the planet's magnetic defenses, potentially collapsing the entire global power grid for weeks, not just days. The real punchline comes down to pure economics, and it is a number that should make you feel deeply unsettled. According to NOAA's Space Weather Prediction Center, a direct hit from a G5 storm could cause an estimated $1 to $2 billion in damage every single day in the United States alone. This chaos would come from disrupted GPS signals grounding flights, failing communication satellites, and burning out transformers, a financial toll equivalent to a Category 5 hurricane making landfall every day without ever moving on. So the question is no longer whether these storms exist, but whether we are ready for the one that is already on its way. Venus, for starters, is a world that sounds like a punishment from an ancient myth. Its surface temperature holds steady at 465 degrees Celsius, a heat so intense it would melt lead, while the atmospheric pressure at ground level is 92 times what we feel on Earth, a crushing weight equivalent to being nearly a kilometer under the ocean. The greenhouse effect there has run so completely out of control that the planet is actually hotter than Mercury, even though it orbits 50 million kilometers farther from the Sun, a fact confirmed by NASA in 2023. Now let's shift to Mars, a place we once dreamed of as a second home. In June of 2018, a global dust storm began to swell, and within weeks it had engulfed the entire planet in a haze so thick that sunlight could not reach the surface for 10 straight days. The Opportunity rover, entirely dependent on solar power, lost contact with Earth on June 10th of that year, and despite months of listening, NASA officially ended its mission in February of 2019, a silent death by weather. Then there is Neptune, a distant blue giant that defies every intuition about cold and distance. It sits roughly 4.5 billion kilometers from the Sun, yet its winds scream across the planet at 2,100 kilometers per hour, the fastest recorded anywhere in our solar system. That is more than 8 times the speed of a Category 5 hurricane, a supersonic jet stream tearing through a methane atmosphere. How does a world so far from the Sun generate such fury? The answer lies in the fact that these aren't anomalies, they're the norm. The solar system is not a calm neighborhood with a few storms. It's a collection of extremes designed by physics to push every boundary we think we understand. Venus is a furnace with an atmosphere heavier than any deep ocean dive. Mars is a frozen desert swept by planet-wide dust plagues. And Neptune is a supersonic wind tunnel at the edge of darkness. Each one mocks the idea that our own planet's weather is dramatic or dangerous. When we measure the destruction of a hurricane by the number of homes it flattens, we are measuring our own fragility, not the true scale of these forces. So, what makes Earth so special that it became the only known oasis in this cosmic nightmare? That might be the most extraordinary fact of all. So, what makes Earth so special that it became the only known oasis in this cosmic nightmare? Jupiter spins faster than any other planet in our solar system, completing one full rotation in just 9 hours and 55 minutes and 30 seconds. That dizzying speed generates a centrifugal force strong enough to make the entire planet bulge outward at its equator. The result is a world that is visibly wider around its middle, a shape that sets the stage for everything else we have explored. This rapid rotation does not just distort the planet's silhouette, it actively drives its turbulent atmosphere. The planet's visible bands, the bright zones and dark belts, move in opposite directions at different latitudes, creating immense friction where these opposing currents meet. That friction is so powerful that it churns up the violent storms we have been discussing, some of which have raged for decades without losing their ferocity. So when you see those striped clouds in a telescope, you are looking at the direct consequence of a planet spinning at breakneck speed. To make sense of this, try picturing Jupiter as a giant spinning top, but one made entirely of gas. Now imagine that the surface of this top is covered in countless parallel streams, some flowing east, others flowing west, all at different velocities. Wherever two streams collide, they do not simply cancel each other out. They whip up swirling eddies, and some of those eddies grow into the colossal systems we have been analyzing. Without the planet's extreme rotation rate, those contrasting bands would not exist, and neither would the Great Red Spot. None of this was understood when Galileo Galilei first pointed his telescope at Jupiter in 1610. What he saw were 4 small points of light dancing around the planet, and those moons convinced him that not everything in the heavens orbited the Earth. That single observation shattered the geocentric model and launched a new era of astronomy. But it would take 4 more centuries before a spacecraft could get close enough to measure the real physics at work. The Juno mission has been doing exactly that, mapping the planet's gravitational field with unprecedented precision. And what Juno has confirmed is consistent with everything we have learned. This is a world defined by speed, pressure, and extremes. When you combine a 9-hour day with opposing bands of clouds and a hidden metallic hydrogen core, you get a machine that generates weather on a scale our planet simply cannot replicate. So the next time a forecast calls for a Category 5 storm, just remember that on Jupiter, that would be considered a calm afternoon. We measure our storms by destruction. We name them, track them, and brace ourselves for their impact, knowing that a single Category 5 can flatten a city in hours. Yet, if you could lift one of these terrifying tempests and place it gently on Jupiter, it would vanish without a trace, a whisper of wind lost against a churning world. The scale of the universe's violence operates on a plane so far beyond our daily experience that our language fails to capture it. We see a hurricane as a monster, but on Jupiter, a planet of liquid metallic hydrogen, storms are not merely weather events, they are expressions of the planet's very core. They churn in a process where heat from the interior, not the sun, drives colossal convection currents, creating a surface of swirling bands and vortices that stretch for tens of thousands of kilometers. Even the fastest winds we have ever recorded on Earth, which hit around 400 kilometers per hour, are slower than a casual breeze on Neptune. We can only grasp this alien reality through the improbable success of our own machines. The Juno probe, a spacecraft encased in a 180-kilogram vault of solid titanium, has been our lone emissary to this world since 2016. It has dived through radiation belts 100 million times stronger than a dental X-ray and emerged with 30 terabytes of data that have rewritten our understanding. What we have learned is a catalogue of extremes. Temperatures at the poles reaching 700 degrees Celsius, immense auroras powered by volcanic ejecta, and a gravity field that reveals a planet without a surface. The sheer scale of these 10 years of discoveries shows us a place where physics is performed in extremes, a realm that seems almost intentionally hostile to the fragile chemistry of life. This constant assault of hostile numbers, the overheated atmosphere, the diamond rain falling into a furnace, the radiation that would kill us instantly, paints a humbling picture. It is easy to forget that our next-door neighbor is a furnace, or that another is a toxic shroud when we are so comfortable on this calm blue rock. Our planet is a rare, sheltered corner of the solar system, a thin haven between the vacuum of space and a molten core where the pressure is just right and the temperature is tolerable. But a single glance beyond our fragile atmosphere reveals the rest of the cosmos as a perpetual nightmare, a place where the laws of nature conspire to create chaos on a scale we can barely comprehend. So, what would happen if you dropped the most powerful hurricane on Earth into the Great Red Spot? It would be a speck of dust thrown into an ocean storm. It would be a brief, insignificant ripple in a tempest that has raged longer than any nation on our planet has existed. It would be nothing more than a moment of turbulence in a corner of a vast system, a tiny reminder that our worst fears are simply the signature of a universe that is magnificently, terrifyingly, and eternally indifferent.